So in section 4 we'll talk about the Laplace transform and its applications, and we'll start with the definition of the two-sided Laplace transform. Well, it's a Laplace transform for a signal f of t that can be potentially non-causal. This is why we have here an integration limit that starts from minus infinity. Okay, so the Laplace transform of the function f of t is computed by this expression over here, where s is the Laplace variable and it's constructed as a Cartesian complex number. The real part is sigma. It will be called the damping factor, and the imaginary part will be j omega, and it will be, well, a function of the frequency. In English we use frequency both for frequency expressed in hertz, okay, f, and for frequency expressed in radians per second, and that's the omega. Sometimes we say angular frequency for omega, but most of the time we say frequency, and it's clear from the context if you mean omega or f. In French we use the words pulsation and fréquence respectively for omega and f. Okay, so s is the Laplace transform. So this thing here with s defined over here is kind of a complex exponential. Okay, so this integral will not be defined everywhere. We'll say that it is defined in the s that are in the region of convergence. So the region of convergence is the region where this integral exists. Okay, s is a complex number, so we'll say that the region of convergence is a part of the entirety of the complex plane. So there is also a definition for the inverse Laplace transform, and it allows you to compute f of t from its Laplace transform, capital F of s over here. This inverse Laplace transform can be computed using complex integration, but that goes far beyond the scope of this course. So what we'll do is use algebraic methods, okay, partial fraction decompositions, and then using tables of transform to go from f of s to f of t. We'll see in a few slides that this equation is somehow important if you want to understand, well, the insights that are behind the Laplace transform. So the Laplace transform converts the function f of t to the s domain, and it can be converted back again to the original time domain. So there is a one-to-one relation if you take into account the region of conversion. So if the function that you're considering is the impulse response of a system, you remember that the impulse response characterizes the system in the time domain. Well, the Laplace transform of the impulse response will be called h of s, and it will be called the transfer function. We'll come back to that later in the course, and without a surprise, well, h of s will also characterize the system in the s domain, and the roots of the denominator, which we'll call poles, will also be very important. If f of t is just a signal, we call f of s its Laplace transform. So in this slide I will attempt to give you an idea that is behind this Laplace transform, and for that we use the inverse Laplace transform. It's not necessary to know, of course, this formula. For instance, in the explanation the factor doesn't matter, and also the integration bounds do not matter. What is important is what is over here and the fact that you have an integral. So I want to compare this inverse Laplace transform with two things that we will see further on in the course. The first one is in the Fourier series, okay, and the other one is the inverse Fourier transform, and it's kind of given here in gray just to tell you that you haven't seen this, but please come back to this slide when we have seen the theory behind these two concepts. What does the Fourier series and the inverse Fourier transform do is decompose the signal f of t in an infinite sum. Here it will lead to an actual infinite sum where you have, well, frequency that is kind of a discrete variable. It's k times the fundamental. This will lead to a discrete spectrum, and here we decompose f of t in terms of frequencies, but you'll have a continuum. Okay, so the frequency variable will be continuous. So you see here exponential signals of purely imaginary arguments. Okay, so this means that if you take these two over here, you will have a cosine with the appropriate argument plus j times the sine with the appropriate argument. This is true for this one and this one. So what we do in these two transforms is decompose the signal as a sum, this is how you can see it, of sines and cosines, and to each sine and cosine you assign a certain weight. The weight over here will be this coefficient, which will be the Fourier coefficient, and here in this continuum the weight is what is called the Fourier transform. Well, in the Laplace transform you do something very similar, but you decompose your function f of t as a sum of complex exponentials. Okay, and if we write this over here with s is equal to sigma plus j omega, we can write this as e of sigma t e of j omega t. Okay, so these are damped cosines and sines. So in this sense the Laplace transform is more general because it decomposes the function of time into a sum of damped sines of cosines with varying frequency and varying damping factor, and each damped cosine has a certain weight, and this weight will be the Laplace transform. So in this course we'll mostly work with one-sided Laplace transforms because we consider either f of t that is causal, or we consider signals that have been made causal by multiplication with the unit step. Remember that if you take a non-causal function f of t and you multiply it by a unit step, the resulting function, this one here, will always be causal. Well, if you take the Laplace transform something that is causal, you know that it's 0, right, to the left of t equals 0, so it makes no sense to integrate from minus infinity. You might as well start from 0. Okay, and here again you find this 0 minus. We'll see in the next slide that this means that you have to be a little bit on left of 0. Okay, and this is for one particular function, and to compute its Laplace transform, it's the delta, the Dirac delta. So we obtain the one-sided Laplace transform by simply integrating from 0 to infinity, and for the Dirac impulse, and when f of t is the Dirac impulse, we'll have to put a 0 minus over here. So we use the one-sided Laplace transform because, well, we deal in applications mostly with causal systems and signals. Okay, anyway, if the signal f of t is causal and you need its Laplace transform, it doesn't matter if you're using the two-sided or the one-sided Laplace transform because they will coincide on a causal system. There is a difference only if the signal is non-causal. Then a word on this limit here. Integration limit is 0 minus. 0 minus is 0 minus epsilon, which corresponds to a value to the left of 0 by an infinitesimal value epsilon. Okay, and this is because at some stage we'll have to integrate things that contain a delta. Okay, and you know that if you integrate a delta, you have to do this. This will be 1, of course, but you have to stay on the left of 0. Okay, so if you take 0, you'll have problems with the definition of the one-sided Laplace transform. So this is why we consider this 0 minus. For other functions different than the Dirac impulse, you can just consider the integration bound to be simply 0. We'll see that another advantage of the one-sided Laplace transform is that it's used to obtain the solution of differential equations when you have initial conditions. So we've just seen that the Laplace transform of f of t, let's write it like this, is the integral from 0 to infinity of f of t e to the minus st dt. S is equal to sigma plus j omega. And the region of convergence, okay, of a causal function, this is normal because we are using one-sided Laplace transform. This region of convergence, well, will be the region of the complex plane where this integral converges over here. Okay, and you can show, this will be done in the next slide, that this region of convergence is the set of all s that can be written sigma plus j omega, such that this integral converges in over here. Okay, and what is interesting about it is that this expression does not depend on omega. Okay, so the region of convergence is independent of the frequency. So if we make a drawing of the complex plane, the S-plane, the Laplace plane, it has several names. Okay, so here we can call it real part of S. So this is sigma. Here we'll have the imaginary part of S. So this is j omega. We can have a look at the shape of this region of convergence. You can see that when sigma becomes large, well, this will dampen the signal f of t. Okay, so the larger sigma gets, the more chance you have that this integral is going to converge. So if sigma becomes large enough, at some stage this integral will start to converge. Also, it's not this formula is not affected by omega, so it's independent of omega. So this means that the region of convergence will look like this. It will be to the right of some value here, sigma. Let's call it sigma min. And to the right of that, you have that this integral over there converges. Okay, so for the domain of the region of convergence of the Laplace transform of a causal function, it will always be something that is to the right of a minimal sigma. And now we'll show this result over here. So we are looking for the region of convergence of the Laplace transform. So we are looking for the S such that this integral converges. Okay, so what we'll do is take the absolute value of the integral. Okay, so what we do to go from here to here is write S is equal to sigma plus j omega. And since you know the properties of the exponential, you know that you can rewrite it like this. And now for the second time, we'll use this relation here, this inequality. The absolute value of the integral of f of t is smaller or equal than the integral of the absolute value of f of t dt. And if you use this inequality, you can, well, bound this thing over here by this thing. So this is an upper bound of this thing over here. Here we have a complex number under polar form, and the modulus, well, is 1. Okay, so we obtain that this here is an upper bound of this, and if this quantity is bounded, okay, well, obviously this quantity will be bounded also, and the Laplace transform will exist. So if this function here is absolutely integrable, the Laplace transform will exist. Okay, and well, by appropriately choosing sigma, it's often, not always, often possible to make sure that this integral will converge. You have to use sigma large enough. Okay, and this is the case even if f of t is not always itself absolutely integrable. It says here often. Why? Well, but there are exotic functions that you will not encounter in practice. But if you take this one here, e to the t square, well, you will not be able to find a sigma that will make this integral converge. Okay, but we'll say that for most functions that we'll use in practice, it's always possible to find an appropriate choice for sigma. So here we have shown that if this is bounded, okay, this integral is bounded, then the Laplace transform exists. It's also possible to show that this is a necessary condition, but this is more complicated, so we will not do this. Well, let's try this on a very simple causal function, which is shown over here. It's an exponential function, and we assume here that a is negative, so that it has this form over here. Okay, so we can have a look at the region of convergence of the Laplace transform of this function, and we have just shown that it is given by this set over here. It's a set of S such that this integral converges. Okay, so let's have a look at this integral. We can write it like this. So this is f of t. Okay, and since everything is positive over here, we can forget about the absolute values, and knowing the properties of the exponential, you can write it like this. Okay, and for this integral to converge, we need sigma minus a. Let's write it a bit more clear. Sigma minus a larger than 0. Okay, so this integral converges indeed for sigma larger than a. So as we had anticipated, the domain or the region of convergence is to the right of something, and here it's to the right of A. Okay, remember here that A is negative. So the domain of convergence is to the right of A. Okay, and we see indeed that this domain of convergence does not depend on omega. So remember that we had this set of functions in the previous sections. What we'll do now is take the Laplace transforms of these signals, and we'll start with the Dirac impulse. So the Laplace transform of this Dirac impulse is given by this expression, and for the Dirac impulse we've said, well, that you need to start integrating a little bit to the left of 0. This is what this 0 minus is meaning. Okay, so let's try to compute this, and for this we'll need the shifting property, and I'll write it again in its general form. So what we'll have here, it's a delta located in t0. Well, we'll have to evaluate the function in t0, and you'll have a delta at the same spot. Okay, if you multiply this, it will be 0 everywhere except at t equals t0. Okay, so this is how you obtain this shifting property. And here my function, okay, f of t will be e to the minus st, and the t0 that I will be considering will be 0. Okay, so if I use the shifting property, I replace this thing over here by this thing over here. So it's my f of t evaluated in 0. This is a 1 over here, and we know that the area below a delta is 1. Okay, so the Laplace transform of a Dirac impulse is 1, and there are no restrictions on the region of convergence. So the region of convergence is the whole S-plane, the whole Laplace domain. So let us continue with the unit step function, or the Heaviside function. Okay, so the definition of the Laplace transform is given over here. You integrate from 0 to infinity, but on this interval, of course, the unit step is 1, so you can rewrite it like this. If you integrate this, you obtain this thing over here that you have to consider at the integrating limits 0 to infinity. So this one will give a 0, okay, and you'll have 0 minus 1 over s. So this is indeed 1 over s. The Laplace transform of a unit step is 1 over s, but we still have to look at the region of convergence. Remember that the region of convergence will be OS sigma plus j omega, such that, well, this integral here from 0 to infinity f of t e to the minus sigma t dt will converge. Okay, well, if we replace f by the unit step, this will become an integral 0 to infinity of e to the minus sigma t. I can leave out the absolute values, it's positive dt smaller than infinity. Okay, and you can see that if you choose sigma positive, then in this integral will converge. So the integral converges if the real part of s, that is sigma, is larger than 0. So the region of convergence is the open right left of plane. So if we call this thing here the real part of S, sigma. This is the imaginary part of S. It's equal to j omega. Then the region of convergence will be to the right of the imaginary axis. But what we mean by open right of plane is that you can't take the imaginary axis. So it's to the right of the imaginary axis. So let us continue with our library of Laplace transform and continue with the unit ramp. And the unit ramp can be written like this. So by definition of the Laplace transform, you obtain this equation. We are integrating over 0 infinity, and over this interval, well, the unit step is simply 1. So we end up with this integral that we have to compute, and well, we have to use integration by parts. Okay, so remember that VW, if you take the derivative, is V prime W plus VW prime. So you can write VW prime, that's the derivative of VW, minus V prime W. So if we integrate now, we have that the integral of VW prime is equal to VW minus the integral of V prime W. In this case, V will be t, V prime will be dt, W prime will be e to the minus st dt, and W will be the integral, so that will be e to the minus st over minus s. Okay, so now we can use our formula. So this is indeed the integral that we are interested in. It's the product of this one and this one, dt. So this is indeed VW prime. Okay, so this will be VW, and this will be the integral of V prime W. Okay, this one will not give any contribution. At infinity, this term will make it 0, and at 0, this factor will make it 0, and at 0, this t over here will make it 0. So this does not give any contribution. So we have to compute this term. It's a minus sign because you have a plus sign because you have a minus sign over here and a minus sign over here. So we need to compute this integral. So if we integrate this function over here, this is what we obtain with a minus sign, and we have to consider it at the limits 0 infinity. So this will be 0 minus 1 over s squared. So indeed the Laplace transform of a unit ramp is 1 over s squared. We have to obtain the region of convergence, so we have to consider the sigmas for which this integral will converge. Okay, so we can rewrite it. T e to the minus sigma t. Normally you have absolute values here, but you can forget about those because everything is positive. So this integral needs to converge, needs to be bounded. And you see that as long as you have a sigma that is larger than 0, this integral will converge. So the region of convergence is the same than the one we had obtained for a unit step. So let us continue with our catalog of Laplace transform, and now we are going to compute the Laplace transform of a real exponential function. Okay, this is a function that we have already considered, but not for the Laplace transform. We've used it as an example to compute the region of convergence, and we had seen that the region of convergence for this type of function was sigma larger than a. So it's the open half plane to the right of sigma is equal to a, right? But we haven't yet computed the Laplace transform. So let's use the definition, and the definition yields this expression. As usual, we are going to integrate between 0 and infinity. So in this interval, this is just 1, and we end up with this expression over here. Remember that we can, using the properties of the exponential, rewrite things like this. So we integrate this. This is what we got, and the integration limits are 0, infinity. This one is not going to contribute, so we'll have 0 minus 1 over s minus a. So this is the Laplace transform of a real exponential function. And we knew that the region of convergence is sigma larger than a. You can do the same thing here with a complex exponential. Okay, so with a complex number, and you'll obtain exactly the same expression. The only difference is in the region of convergence. You have to write sigma larger than the real part of a. A is now a complex number, and sigma, well, must be larger than some real number, and this real number is obtained by taking the real part of a. So what we'll do here is take a is equal to j omega 0. So here a is a purely imaginary number, so the real part of a here is equal to 0. Okay, so if we apply the formula and we compute the Laplace transform of this complex exponential, well, we obtain this formula over here where we put a is equal to j omega 0, and this is the resulting Laplace transform. Okay, and we obtain also the region of convergence. Sigma is larger than the real part of a, and the real part of a is 0 over here, so we have this region of convergence. This is very important because we'll use it to compute the Laplace transforms of a sine and a cosine. So let us take the Laplace transform of another real exponential signal, this one over here, and you might remember that this signal is the impulse response of a first order system. Okay, and we'll see later that if you take the Laplace transform of this one, you end up with its Laplace transform, and it's the transfer function of a system, and we'll come back to that later. But this explains why I'm interested in taking the Laplace transform of this signal over here. Okay, so we'll remember what we have found in the previous slides. The Laplace transform of this signal over here is equal to 1 over s minus a, right? And the domain of convergence was sigma larger than a. In this case, a is equal to minus 1 over t, right? And there is also, well, a gain in front. We'll see later that the Laplace transform is linear, so what we can do is take it out. Say, if you do that and taking into account the results that we've obtained previously, we'll see that the Laplace transform here will be k over t divided by s minus a, but a is minus 1 over t, so we'll have minus minus plus 1 over t. If we multiply on the numerator and denominator, we have k t s plus 1, and this is h of s, and this will be the transfer function of a first order system. Again, we'll come back to that later. Okay, of course you can go through the calculations using the definition of the Laplace transform and you'll end up with the same result. Of course, the domain of convergence will be sigma larger than a, and a here is minus 1 over t. So these are the 5 one-sided Laplace transform that we have obtained so far in the course. You should be able to obtain these transforms from the definition of the Laplace transform together with the region of convergence that is associated with each Laplace transform. At the time of the exam, you won't have access to this table, so you will have to re-obtain these Laplace transforms yourself from scratch from the Laplace transform definition. So in this slide we introduce the concept of a pole and of a zero. So let's take the Laplace transform of the function, time function f of t. It will be f of s, and in general, as we've seen in several examples now, what we'll have is a rational function in s. So you'll have a numerator polynomial and a denominator polynomial in s. What is called a zero of f of s is a value of s for which f of s is equal to 0. So it's a root of the numerator polynomial. So that's a 0, okay? And in this course we'll not talk a lot about zeros, but it has implications in courses that you might follow in the future. What we'll use extensively is the concept of a pole. A pole of f of s is a value of s for which f of s tends to infinity. So it's a value of s that is a root of the denominator polynomial. Poles and zeros can be complex. If they are complex, there will be complex conjugate pairs, because the examples that we'll consider will have numerators and denominators with real coefficients. Okay, and you see that for s that corresponds to a pole, f of s tends to infinity. So by definition of the region of convergence, there can be no pole in this region of convergence. So here we'll consider the Laplace transform of f of t. It will be f of s, right? And this f of s as poles, we'll call them pi here, and the real part of pi will be called sigma I. Okay, so this is what is written over here. So let us first take the case of an f of t that has finite support. Remember that a function with finite support will have t1 here, t2, and you know that outside the interval t1, t2, so here this function is 0, okay, and here in the middle, all kinds of things can happen, okay. And remember that the Laplace transform is an integral from minus infinity to infinity of f of t e to the minus st dt, right? This is f of s, this is here f of t, and let us draw maybe an example of such a function. Voila, I should do it in blue. This is an example. Well, if we take the Laplace transform over here, we can change the bounds, because here the function is 0, there it is 0, and we can do integral from t1 to t2. So as long as the function here in between t1 and t2 does not go to infinity, and that it is well behaved, this integral will always converge. Okay, this is why a function of finite support will have a region of convergence, which is the whole S-plane. You do not expect problems of convergence when you're computing the Laplace transform of this kind of function. Okay, so for other functions, and the other functions that we'll consider are causal functions, and we'll consider a function that we've already considered before. Okay, and it's the real exponential function. This one, and it's this function here, ut to make it causal, and here a is negative. And we've seen that the Laplace transform is 1 over s minus a, right? And that the region of convergence was sigma larger than a. Okay, so what you see here, the pole is a, and you see that the region convergence is to the right of the pole. So this you can do in general. So if you have a function and you have its Laplace transform, you look at all the poles. Okay, and let us take an example here, sigma j omega. So this is the real part of s, here it's the imaginary part of s, and let us suppose that you have poles over here. So here I have a complex conjugate pair, I have a pole over here, another one over here. Well, then you can look at the pole with, or the poles here in this case, with the maximum real part. Okay, it will be these poles over here, and then the region of convergence is to the right. Okay, so this is the region of convergence. So whenever a function is causal, you look at the poles, and the region of convergence will be to the right of the poles with a maximum real part. So we have already seen an example of a function of finite support that has region of convergence, which is the whole S-plane. Okay, well, it was the Dirac impulse. Okay, delta t. By definition, this function here that I'm drawing as a finite support, right? And we have seen that indeed the Laplace transform f of s is equal to 1, and that the region of convergence was the whole S-plane. So this is an example of this. So what I've done here is skip quite a few slides about the Laplace transforms of non-causal functions and their region of convergence. So the interested student will have a look at that, but this is not crucial for this course, and of course at the time of the exam I won't mention this. Well, let's start with the properties of the Laplace transform, and the first interesting property is that the Laplace transform is a linear transform. So this means that if you know the Laplace transform of f of t, f of s and the Laplace transform of g of the g of s, you can also obtain the Laplace transform of a linear combination of f of t and g of t with the coefficients alpha, beta, okay? And this Laplace transform is simply the linear combination of the corresponding Laplace transforms. The region of convergence of this new function here is the intersection of the regions of convergence of the initial Laplace transform f of s and g of s. So this is kind of interesting. So if you know the Laplace transform of f of t and Laplace transform of g of t, you can come up with the Laplace transform of linear combinations of this Laplace transform. And this is how we'll find the Laplace transform of a sine and a cosine. So now we need to extend our catalog of Laplace transforms, and we'll do that by, well, considering or by obtaining the Laplace transform of a cosine. And in the next slide we'll obtain the Laplace transform of a sine. Remember that we have found that the Laplace transform of this complex exponential, here we have a purely imaginary number, okay, is given as by this equation over here, and that the region of convergence is this one. Okay, so we know, or you should know by now, that the cosine can be rewritten as a half e to the g omega 0 t plus e to the minus j omega 0 t. This is the Euler identity. Okay, so if we stick that in here, we obtain this relation. Okay, we know the Laplace transform of this signal, and we know the Laplace transform of this signal. So we can go to this equation, and this is simply by linearity of the Laplace transform. Okay, so this Laplace transform is given over here, and this Laplace transform is given over here. Okay, so now it's just a matter of putting everything under the same denominator, compute the product of these two, okay, they're given over here, and do the math, and you obtain the Laplace transform here of a cosine. And you know, since you have used two Laplace transforms, they both have region of convergence sigma larger than 0. Well, the intersection will remain the same, so the region of convergence for the Laplace transform of a cosine is the open right half S-plane. This means that it's to the right of sigma is equal to 0. Well, here we do something very similar but for the sine, okay, and the only difference is that the plus has become a minus over here, and instead of having 1 over 2, it's 1 over 2j. If you go through the calculations, you'll see that the Laplace transform of a sine is given by this expression with, again, the same region of convergence. Okay, so at the time of the exam, you won't have the tables with transforms. I expect you to be able to recompute the Laplace transform of a sine. So this is now the table of transforms with all what we have done so far, and again you should be able to obtain these transforms and the associated regions of convergence from the definition of the Laplace transform. You see that there are two more columns. Well, we'll see two more major properties of the Laplace transform that will allow you to extend the catalog of Laplace transforms. So let us start with the first property, frequency shifting, that will allow us to extend our catalog. So we start from a function f of t, and its Laplace transform is f of s, and here we take a real lambda, and what we do here is indeed frequency shifting. Okay, if lambda is positive, we shift everything to the right in the Laplace domain, and if lambda is negative, we shift everything to the left. This is what this is saying. Okay, by the definition of the Laplace transform, you can rewrite this as follows. We have just, well, replaced s by s minus lambda. This is what we have here. This over here, by the properties of the exponential, can be rewritten as e to the minus st times e to the lambda t. And now we can reorganize things. We have reorganized it in such a way with a big parenthesis here to show you that this is actually a Laplace transform, but the Laplace transform of this function over here. Okay, so we obtain this expression here is equal to this expression. So this means that if you multiply in the time domain by an exponential, that will dampen, or to the contrary, that will multiply the function with a growing function, what happens in the frequency domain is that you shift. Okay, well, the region of convergence, obviously if you shift in here, will also be shifted if you compare it to the original region of convergence of f of s, and the region of convergence of this one will be shifted to the right if lambda is positive, and it will be shifted to the left if lambda is negative. So let us see how we can use this frequency shifting property to extend the catalog. So remember that the Laplace transform of f of t ut is equal to f of s. This is the starting point, and we kind of ask the question, what is the Laplace transform of this same function but multiplied by this exponential here, u of t? Well, we've seen that everything will be shifted in the Laplace domain. Okay, so there is also a corresponding shift of the region of convergence. So let's use this, and in this case here what we'll do is simply take f of t is equal to 1, and then we have Laplace transform of u of t that we know is 1 over s, and the domain or the region of convergence is sigma larger than 0. And let us now look, if we apply the property, at the Laplace transform of e to the lambda t u of t, and this will be, by the frequency shifting property, 1 over s minus lambda. Okay, and the region of convergence will be shifted by lambda, so we obtain this region of convergence. Okay, well, this is what is written over here with lambda is equal to a. Right, here we have produced something that we had encountered before, so it's nothing new for our catalog, it's just a way of obtaining it differently. Let us now consider f of t is equal to t. Okay, so we have here the Laplace transform of t ut. This is the ramp signal, right? And this is 1 over s square, and again the region of convergence is sigma larger than 0. Let us now apply this frequency shifting property. So t e to the lambda t u t, and this will yield 1 over s minus lambda squared, and the region of convergence will be shifted by lambda. Okay, So this is what we see over here again with lambda is equal to a, and this is something that we can add in our catalog. It's new, right? So here we have two new functions that we can add in our catalog. I'll just show this one here, and I'll leave the other one as an exercise. And what we'll do over here is use f of t is equal to sine omega 0 t. The Laplace transform of sine omega 0 t ut is omega 0 s squared plus omega 0 squared, and the region of convergence was sigma larger than 0. We can apply now the property. We take this same sign and rewrite e to the sigma 0 t ut. So here we have directly used lambda is equal to sigma 0, and what you have to do is take this one and shift everything by sigma 0. So this will give us s minus sigma 0 squared plus omega 0 squared. The region of convergence will be shifted by sigma 0. This is what we obtain. This is what we see over here, and you can also factor the denominator and you obtain then this expression over here, in which you see that the poles are sigma 0 plus minus j omega 0. So here I want to make the link with something that we've seen in section 2 at the end, where we had considered this complex exponential function, the exponential of at ut, where a was complex and was equal to sigma 0 plus j omega 0. Okay, and we had seen that you can obtain this signal over here by taking the real part of this signal over here. But another way to see this was that this signal is f of t plus its complex conjugate, and the whole thing multiplied by a half. Okay, so you can review this in section 2. That's the advantage of a video course. And here the complex conjugate of f of t, it's the exponential of a conjugate times t, the whole thing times u of t, and the complex conjugate of a is sigma 0 minus j omega 0. So this signal over here, it's the sum of a complex exponential, okay, that involves a, plus a complex exponential that involves a conjugate. Okay, so you see here that the Laplace transform here is this expression over here, but you see that the poles are sigma 0 plus minus j omega 0, and you see that they are linked to a and a conjugate. So remember that we can also obtain the region of convergence by looking at the pole or at the poles and taking the region of convergence to the right of the pole with the highest real part. Okay, so let's apply it to this real simple example. So let's draw the complex plane. So this is sigma, real part of s, j omega, the imaginary part of s, and let's for instance take a negative a, then we have a pole over here, and the region of convergence will be to the right of this pole. Okay, this indeed corresponds to what we had said in this case the region of convergence is sigma larger than A, right? For this example, it will be the same. What you will have is that you will have here on top a second pole at the right spot. So this will lead to the same region of convergence. Okay. So for these two examples here, let's draw the complex S-plane. So here we had taken A negative, okay, so this is sigma and this is j omega. This is the S-plane, and let us draw the two poles, and the poles here are complex conjugate. Remember, the poles are sigma 0 plus minus j omega 0. And here we'll assume that sigma 0 is negative. Okay, so the real part, and this is sigma 0 over here, and what you have here is j omega 0, and here minus j omega 0. Okay, so these are the two poles, and if you look at the region of convergence, you take all the poles and you take the ones that have highest real part, and since we only have two complex conjugate poles, the real part will be sigma 0, and we have to take to the right of that, and this is the region of convergence, and this is indeed what we had obtained, right? The region of convergence was sigma larger than sigma 0. So we can now extend our catalog of Laplace transforms. So these are all Laplace transforms that we have obtained here from the definition of the Laplace transform, and these two we have obtained using the property of linearity of the Laplace transform. So this is the original transform, okay, and in the second column we give all Laplace transforms that we can obtain using the frequency shifting property of the Laplace transform, starting from Laplace transforms that are in this first column over here, and we've seen that we have obtained 4 of them. One of them is a Laplace transform of the exponential signal that we had already obtained, but differently previously using the definition of the Laplace transform. So again, you should be able to obtain all these transforms over here, starting from the definition of the Laplace transform and all the properties, and you should also be able to produce the region of convergence. So you've seen that in this table of Laplace transform there is a third column, and this third column will correspond to Laplace transform that have been obtained using this second very important property, which is the property of time shifting. Okay, so again we'll start from the one-sided Laplace transform of f of t, and it will produce f of s, and we'll ask the question, what happens if we do time shifting by the quantity tau over here? So let's try and put this in a graph. So what we'll first do is represent the system, or the signal, sorry, f of t ut, and we'll draw it like this. Okay, so ft ut is indeed causal, and this is ft ut, and if you, well, translate it or time shift it by the quantity tau, you'll obtain something that looks like this signal over here, and this is ft minus tau ut t minus tau. It's important that you multiply by this shifted unit step to make sure that everything is 0 to the left of t is equal to tau. Okay, so this is why you need to do a time shift on both f and u of t. So let us take the Laplace transform of this shifted signal, and by definition this is what you obtain, right? We've seen here that to the left of t is equal to tau, everything is 0 for this time shifted signal. So it means that you can start integrating from t is equal to tau over here, and that we can forget about this shifted unit step. So this is how we obtain this expression over here. And what we'll do now is use the substitution. T bar is equal to t minus tau, so obviously t will be t bar plus tau, okay, and dt will be equal to dt bar, okay. So this is t bar. Obviously e to the minus st will be using this expression over here, e to the minus s tau, e to the minus st bar, okay. And we'll do a change of variables, okay. So here we have the integration bounds tau and infinite, okay. So using this change of variables, this is changed to integration bounds 0 infinity, right? And e to the minus st, well, you have this factor, you find it over here. We can take it outside the integral because it does not depend on t bar, and the other factor has to stay inside the integral because it depends on t bar, okay. So we have rewritten everything like this, but here you see that this is the Laplace transform of the signal f ut. So it's the Laplace transform of the original signal over here. So we see that the Laplace transform of the time shifted signal is replaced by this quantity over here. So it's f of s multiplied by the exponential of e to the minus s tau. So you kind of have a duality here. If you multiply in the frequency domain by an exponential, you do time shifting on the original signal, and if you multiply a time domain signal by an exponential, you do frequency shifting in the s domain. So you see here that to obtain this expression we only use the Laplace transform of the original signal. So obviously the Laplace transform of the time shifted signal will have the same region of convergence. So this is the final table with the Laplace transforms that you should master at the time of the exam, and obviously there are other Laplace transforms that I could add on here, but at the time of the exam I'm really happy if you can reobtain these Laplace transforms from the definition, from the properties of the Laplace transform, and also find the associated regions of convergence. So remember that this table is obtained using the definition of the one-sided Laplace transform. This yields the first column over here, and the two last Laplace transforms involving sine and cosine are obtained from the linearity property of the Laplace transform. Then we have considered the frequency shifting property, and we have applied it to these Laplace transforms to obtain, well, 3 new Laplace transforms in this table. This one over here, this one over here, and this one over here. This one we had already obtained, but differently in the first column using the definition of the one-sided Laplace transform. So here I have added the new property that we have just seen in the previous slide, time shifting. Okay, it's given over here. As said, it's kind of dual to frequency shifting. Here you multiply by an exponential in the time domain and you shift in the frequency domain, and here you multiply by an exponential in the S domain and you do time shifting. Okay, it's very important to not forget this term over here. So what we'll do is use this time shifting properties on, well, these three original transform and these two original transforms that are the sine and cosine, and you obtain, well, very easily the following transform. So I want to stress again that here each time it involves this, well, shifted unit step to make sure that the solution is 0 to the left of t equals tau. So if you do exercises and you have to do the inverse Laplace transform of this quantity over here, do not forget to put the time shift on the unit step. So the next property is the Laplace transform of the derivative of a function f of t, and this differentiation property will be used extensively when we solve differential equations using the Laplace transform. So again, we start from the one-sided Laplace transform of the function, okay, and we have f of s here, and we ask the question, well, what is the Laplace transform of the derivative of this function f of t? Okay, so the Laplace transform of this function over here, and we'll show in the next slide that it is the original Laplace transform times s minus the function, the time function, evaluated in 0. In most cases you'll be allowed to say 0, but in some other cases that will involve the Dirac impulse, well, you'll have to put 0 minus here. So this 0 minus is something that is rather technical. In all the applications that we'll do, practical application, you'll simply be able to replace this 0 minus by 0. Okay, so the Laplace transform of the derivative of f of t is the Laplace transform of the original function times s minus the time function evaluated in 0, and this is how the initial conditions come into play. So let's show that the Laplace transform of the derivative, well, is indeed what we have shown on the previous slide. So what we use here is, well, just the definition of the Laplace transform. Well, the 0 minus is there for these exotic cases where you have Dirac impulse. So as I've said, in practice, just don't mind about this and just put a 0. Okay, I have to put this in the course because it has to be correct in all cases, and this is something that we have to integrate, and we'll use integration by parts for the second time in the course. We'll define v and the time derivative of w, and you can see that this is indeed the integration of, well, v dw dt times dt. Okay, so we have to work by parts. So what we have to do is differentiate this one and integrate this one. This is what we obtain over here. Okay, and this integral can be rewritten as, well, v times w evaluated at the integration bounds 0 minus infinity. So if you multiply these two, the infinity won't give a contribution, that will be a 0. So you'll have minus this function evaluated in 0 minus, and this will produce a 1. So this term over here will give you minus the function, the original time function evaluated in 0 minus. Okay, and here you'll have to subtract the integral of, well, this quantity over here, and if you inject, well, w and the derivative over here, you end up with this integral over here, and that's the Laplace transform of f of t. So that's simply f of s. Okay, and the s that is in here, well, we can take it out because we are integrating with respect to time, and we have a plus sign here because we have a minus sign over here and another minus sign coming in here, so it's indeed a plus. So indeed we found that the Laplace transform of the derivative of f of t is simply obtained from the original Laplace transform f of s, and by multiplying by s and then subtracting the original function f of t evaluated in 0. So we have just shown that if you know the Laplace transform of a function f of t, and that it is f of s, you can easily obtain the Laplace transform of the derivative, and it's obtained by this equation, and it involves, well, the initial condition f of 0. So you need to know the function f of t at the initial condition t is equal to 0. Well, you can kind of use this property to find the Laplace transform of successive derivatives of f of t. So we'll do this for the second derivative of the function f. So the way to go is simply say, well, let us assume that g of t is equal to f prime, the first derivative of t, okay, and that obviously g prime, so the first derivative of g, is, well, the second derivative of t. So if you write this property, what you'll have is s times the Laplace transform of gt ut minus g0. Okay, so g of t is f prime, it's correct, and g0 is f prime evaluated in 0. So now we can use this property over here to replace this over here by the Laplace transform of the original signal minus f0, and if you distribute, you obtain this equation over here. So you see that it's very easy to obtain the Laplace transform of the second derivative. What I very often see at the time of the exam is a variant of that, and this variant is obviously incorrect. It's this version of the equation which is incorrect. So this is very dangerous when you do the exercises, because it means that at the first line you already have made a mistake. So remember that you won't have the tables or the properties at your disposal. You should be able to find this property using this property over here, and if you can do that, there is no way that you can make a mistake. So we can also use the same trick, I won't go into the details, to find the third derivative of the function f of t, and well, looking at this you can kind of imagine what will happen. So it's s cubed f of s minus s squared f0 minus s f prime, first derivative, and I'll have to add the last term over here, minus the second derivative evaluated in 0. So as you can notice, I've skipped a few slides, and they are about properties of the Laplace transform that involve integration. They are there for your information, but since their added value in the course is rather small, I will skip them in this video course. The next property is about the time scaling and the Laplace transform of a signal that has been time scaled. And as usual, I will start from the Laplace transform of my original signal over here, and that's f of s, and we'll ask the question, what happens with the Laplace transform if we do time scaling? Okay, and we'll assume here as usual that it cannot be 0. Okay, so if we use the definition of the Laplace transform, we obtain this equation over here, standard definition of the one-sided Laplace transform. And what we'll do is use the substitution over here. So obviously dt bar will be a dt, okay, or dt is 1 over a dt bar, and we'll have something similar, of course. Here is that t is equal to t bar over a. Okay, so that's t bar over here. Okay, so t, you can replace it by t bar over a, so this is leading to this thing over here. The integration bounds will remain the same, and dt is replaced by 1 over a dt bar. So the 1 over a, we can take it out of the integral, and you immediately see why we need, of course, a different from 0. Okay, and what you see over here is that this is a Laplace transform of the original signal, but with s replaced by s over a. So you can replace this expression here by what you see over here. So you can see that if you contract in the time domain, okay, what you'll have, because of the 1 over here, a over here, you'll have expansion in the frequency domain. And if you do expansion over here in the time domain, you'll do contraction in the frequency domain. So let us illustrate this using a simple example. So remember that the Laplace transform of e to the lambda tut is equal to 1 over s minus lambda. Previously in the course we had written this with an a over here, but I cannot use a because here a is used in another context. So let's take an example of such a function, and I will choose lambda is equal to minus 1. Okay, so the resulting function, we can draw it, and it looks like this, right? So this is t and this is f of t, right? And the Laplace transform of e to the minus t ut, it's 1 over s plus 1. Okay, so what you can do now is time scaling, and let us look at the Laplace transform of the exponential of minus 2t u of t. Okay, so we have used here an a that is equal to 2 in this case, and if you look at this property over here, well, the result should be 1 over 2. Okay, and then you take the original Laplace transform and you replace s by, in this case, s over 2. And if you multiply numerator and denominator by 2, you'll end up with s 1 over s plus 2, and this is indeed what you expect. So you have indeed seen that this formula is indeed correct. So let us draw the function here that is shown. Well, obviously it will go to 0 faster than the signal that is over here. Okay, so here in the time domain, you can see this, we have done compression. And you can clearly see it here in the frequency domain. Here we have done expansion in the frequency domain. Okay, you can also clearly see it from the regions of convergence. So there is indeed an influence on the region of convergence. So this is the real part of S, here the imaginary part of S. The Laplace transform over here will have a pole in -1, and the region of conversion is to the right of that, so this is the region of conversion. And this one over here has a pole in -2, so the region of conversion will be as indicated here in red. And you see that this expansion in the S domain has also resulted in a change of the region of convergence.